Up to now in these videos we've looked at the idea of the spin of an electron in terms of both its angular momentum, h bar over 2, and its magnetic dipole moment, mu. And it was suggested that the word spin would, from now on, be used for either of these. For the electron, the angular momentum and magnetic moment are in opposite directions. But when one changes, the other changes. So if we simply use the word spin, the context should give the sense as to which one is being focused upon. If we're talking about an electron in a magnetic field and we say that the spin is up, or that it's pointing in the same direction as the field, it will be the magnetic moment that we're talking about. The magnetic moment vector will be pointing up or in the direction of the field. If, on the other hand, we're referring to things like the allowed changes in the direction of the spin and therefore engaging with the quantum mechanics of a spin situation, and if things like h bar over 2 come into it, then clearly this will be relating to the spin angular momentum of the electron. The word spin may even be used in a sentence where it could relate to both the magnetic moment and the angular momentum, in the sense that we may well casually slip from one to the other. Providing you're aware of this, then when you hear or see such ambiguities, you should be able to think through what is meant. So simply using the word spin will be my approach in what follows, although now and again I may add the words magnetic moment or angular momentum to the word spin for clarification, and also perhaps because I feel guilty that I ought to. In the earlier videos in this series, we also looked at the simple and obvious idea of classical entanglement, especially for two bar magnets, but also simplistically applying it to two electrons. We then moved on to consider some of the rules of quantum mechanics and their experimental justification. This led us to realize that the entanglement of two electrons could not be as simple and straightforward as the classical entanglement of two bar magnets. We had realized that in dealing with the very small, only sometimes can we say that the spin direction can be known with certainty. For example, the spin of a single electron can, in a way, be known to be in a particular direction, at least in the sense that when the component of that spin is measured in that direction, it must always give the appropriate answer. In other words, it will confirm that the spin could indeed be said to have been in that direction. There will be other situations, however, where we can't say with certainty what the result of a measurement of the component of the spin will be. All we can say is that there will be a chance for this or a chance for that result. And we realize that the mechanics of things at the atomic and subatomic level is not the same as ordinary, everyday, classical Newtonian mechanics. Things definitely behave in strange ways, really strange ways. We looked at trying to explain the entanglement of two electrons by some pseudo-quantum mechanical argument, by trying to apply the basic quantum mechanics rules in a simplistic way. But it didn't really work. What we really need is to get to grips with some quantum mechanics proper. So in this video, number 5, we're going to start thinking about the mathematics that we might later use to get a better explanation of the reality of quantum entanglement. For some people, this will be somewhat oversimplified. For others, it might seem a bit difficult. But stick with it. The way that the mathematics of quantum mechanics has been devised may seem rather odd, but as you use it, you should begin to see, hopefully, the sense in which it predicts these kind of strange outcomes. You get used to its way of working if you stick at it. The beauty of it is that even though quantum mechanics can only deal with probabilities most of the time, the results are correct and have been used to make dramatic advances in physics, particularly, of course, in relation to electronics devices and the like. So, to get into the quantum mechanics, I want to begin this section by making a few definitive statements. First of all, we are going to be talking about an object or a system as being in a particular state. And that word state will be used a lot. We could, for example, be talking about an electron or a group of electrons, but whatever we're considering will be said to be in a given state. In a sense, what we mean by the state will embody the main thing about the system that we're focusing on, and in our case, it will usually mean the spin. The state of the system will then be described by what we call a state vector. And it's unfortunate that we can't really avoid the use of this word vector, because people have a tendency to think about the kind of vectors that we are familiar with in ordinary space. In other words, vectors like force, velocity, magnetic moment even, and things like that. The state vector is not a vector in that sense of the world. It's not something that points in a direction in real space, like the magnetic moment or the angular momentum or a force or whatever. It's not a vector in the 3 dimensions of x, y, z space. The state vector is not in real space. The state vector is the only source of information about the quantum state, and quantum mechanics is the art of using mathematics to extract this information. Physicists say that a state vector, the thing that contains information about the system, can be thought of as being in a kind of imaginary space, and they call it Hilbert space. And even then, however, it's not like it's another world. Rather, it's a mathematical thing. Also, depending on what's being investigated, Hilbert space can be made up of any number of dimensions, not just 3. Fortunately, later on when we discuss spin in more detail, the Hilbert vector space we will need will only be 2-dimensional, at least early on, so things will be kept fairly simple. So that's the first thing to say. If we have a situation in real, everyday 3-dimensional space that we are considering, and if we want to explain it by quantum mechanics, then the first thing to do is to decide the kind of Hilbert space that we need, the kind of space that will contain the state vectors that the system might need to be described by. Sometimes the situations physicists deal with in ordinary 3-dimensional real space may need a Hilbert space made up of lots of dimensions, 4, 5, 6 or more. However, working with spin a half in ordinary 3-dimensional real space will mean, in our case, that we only need a Hilbert space which is 2-dimensional. In talking about the state, or rather the state vector of the system in question, we will mean the thing that exists in this Hilbert space and which contains all the information we need to know about the system we're investigating. If, for example, we're working with spin, as we will be, then the state vector or vectors will contain information about the spin. They won't necessarily have any information about the velocity or the momentum or whatever of the thing that we're dealing with. The imaginary Hilbert space that these state vectors live in will be tailor-made for them, a kind of spin space. If, on the other hand, of course, if I were dealing with a situation where things were moving, where they had velocity or energy or any kind of other variable, then we would assume that the state vectors would contain all the information we would need about those things, or the ones that are important in that situation. The imaginary Hilbert space that those vectors live in would be tailor-made for them, and it would be different to the space for spin, the one that we will need. Obviously, the dimensionality of the Hilbert space will be important. So, if in the real world the system we're investigating could have, say, n independent states, or if you like, there are n independent situations that the system can be in, then we will need an n-dimensional Hilbert space. That imaginary Hilbert space will contain the n state vectors which describe those n situations of the real world. Again, as I've said, we're fortunate, in a sense, that when dealing with the spin of electrons, we can get away with considering only 2 situations, spin up and spin down in the z direction. We will only need, therefore, a 2-dimensional Hilbert space which will contain only 2 defining state vectors with information about the 2 situations. One state vector for an electron with spin up and one state vector for spin down, and both of them will live in our 2-dimensional Hilbert space. When we start to think about entanglement later, and we have 2 electrons, each of which can have spin up and spin down, then we will need to have a higher dimensional Hilbert space and more state vectors, but we'll get into that in due course. Don't worry if that sounds very theoretical and very airy-fairy at this stage. Try to take it on board, and hopefully everything will become clearer as we move through some of the ideas surrounding the mathematics of quantum mechanics. The second important thing to say is that we're going to want to make measurements about a particular situation or the state of the system. We're going to want to measure things about a particular state vector to get the information that's in it out. By that, I don't mean make a practical measurement. We're not talking at this point about actual measurements with apparatus and the like. No, we're going to want to measure things, or rather calculate things, within the mathematics from the state vectors. That's what I mean by measurement using quantum mechanics. For example, we might want to measure the spin direction of a particular state vector. And by that I mean the state vector is written down and contains information about the spin direction, and we would like to use the mathematics to get that information out. In a different type of situation, which we're not really going to be interested in, we might have wanted to measure the energy of the state which contains energy information. So we want to do the mathematical manipulation to get that information out. But again, that won't concern us. We'll be sticking with spin. So the next thing we need to do is to introduce the things that make the measurement in the mathematics of quantum mechanics, and those things are called operators. In quantum mechanics, if you want to make a measurement from a state vector using the mathematics, you need to use the appropriate operator. For example, to measure spin, you need the spin operator. To measure energy, you would need an energy operator, and so on. The basic idea is this. You take the appropriate operator, in other words, the one that represents what you want to measure, and you apply it to, or if you like, you make it act on, the state vector which describes the system you've got, the thing that somehow contains the information you want. Generally, you don't just multiply by the operator, rather you act upon the state vector with the operator. The operator will generally contain some kind of action that will need to be done. So how does that measure anything? Well, if when you do that, you end up with a constant real number multiplying the same state vector, then you can say that you have a measurement, and that the value of the thing that the operator stands for, the measurement, in this case, is the number that you got as the multiplier. So for example, if the state vector here has information about the spin of a particle, and if the operator is the operator for measuring the spin in a particular direction, let's say the z direction, then you can apply that operator to the state vector. And if in doing that you end up with a constant number times the same state vector as before, then that constant number would be the measured value of the spin of the particle, the component of the spin in that direction. By the way, we won't be talking about a measurement of the spin angular momentum here and h⁻², and things like that, although we could be. More usually, however, when we consider making measurements of the spin, we'll mean that if the constant number we get is, say, +1, it would mean it was spin up in the positive z direction. And if the number we get was -1, it would mean it was spin down. It will be as simple as that kind of thing. If, on the other hand, when we applied the measurement operator onto the state, it did not give the same vector multiplied by a real constant number, then we would not have a mathematical measurement. This is true even if, after the operator has acted, the right-hand side made some kind of sense. It may even be a different state. But in that case, if it wasn't the same state as before, then we would not know that the spin was in the z direction, up or down. We would not have a measurement. Don't forget that the operator I'm imagining here is the one which would measure the spin in the z direction, and we'll find out about such operators in a moment. This equation and the idea behind it is very important in quantum mechanics. However, it is not simply for spin, it is the general equation for a measurement in quantum mechanics, and what is measured will depend on the operator used. Obviously, as I've already indicated, in a particular situation with a particular measurement, we'd have to have some more detail about the state vector and the detail about the operator used for a particular measurement. The main detail that we need to get into, of course, will be all about spins. We'll see in a minute that the state vectors for spins that we're going to use will be in the form of simple column vectors, and the operators for measuring the spin will be simple matrices. Now don't worry if you haven't done this kind of thing before. It's fairly easy to get used to the idea of applying spin matrices, that's the operators, to a spin state, that's the vectors, in order to try and get answers to the measurement of the spin in a particular direction. As I say, if the idea of column vectors and matrices doesn't make any sense at the moment, don't worry. Before we can do any of that, we will need to be able to write down something for the spin states, or what we might call the state vectors. We will actually be able to get away with just two of these, one for spin up and one for spin down. This, as I said before, means we'll only need a two-dimensional Hilbert space for these state vectors to live in. We will also, of course, need to be able to write something down for the operators which can be used to measure spin, and we'll need at least three of those so that we can measure the components of the spin in the x direction, the y direction and the z direction. Presumably, if we needed to measure the components of the spin in some other direction in real space, we could combine these operators a bit like we do for ordinary vectors to find the spin operator in a particular direction. These measurements, these spin matrices, these operators, will not be in the Hilbert space. They're simply mathematical operators. Only the state vectors can be considered to be living in imaginary Hilbert space. As mentioned earlier, when I say measure the spin, I only mean measure which direction the magnetic moment is pointing in. I don't mean measure any kind of value for the spin, and I'm certainly not concerned with the angular momentum of h bar over 2, even though it will often determine what's going on. In that sense, what I write down for the state vectors and for the measurement operators don't need to contain a great deal of information. They only need to be concerned with the direction of the spin. However, the same basic rule will apply. If we want to measure the components of the spin of a state or situation in some direction, we will need to apply the spin operator for that particular direction onto the state under consideration, the state vector, and if we get a real number multiplied by the same state vector, then we will have a definite measurement of the spin component in that particular direction, and that measure will be given by the multiplying number. This will be a definite measurement. There'll be no uncertainty about this measurement, and depending on what operator we use for the x or y or z direction, it would tell us whether the spin is definitely left or right if it was x, definitely in or out if it was y, and definitely up or down if it was z. The probability will be 1, a definite measurement if we get this real number multiplier. Our convention will be that +1 will be used as the measure that the spin is in the positive direction that we're trying to measure, and -1 will be used as the measure indicating that the spin is in the negative of the direction that we're trying to measure. So if we're trying to measure the spin in the z direction and we get the measure as +1, it will mean that the spin is up. That's the positive z direction. If we get the real number as -1, it will mean that the spin is down or in the negative z direction. A couple of points then before we dive into this. The system of real space coordinates that we'll use will look like this, where the y-axis is into and out of the screen. The z direction will be upwards for positive and downwards for negative. We may at some point talk about the x or y direction of the spin, but most often we'll only be thinking of a measurement or a spin component in the z direction. The x direction will be left to right with positive x direction to the right. Similarly, the y direction will be into and out of the screen, with positive y direction being into the screen. That's for real space. Also, I suppose, I should emphasize at this point what I will mean by spin direction, especially as we'll be thinking about electrons. As I've tried to hammer home earlier, the magnetic moment of the electron is in the opposite direction to its spin angular momentum, and this is a consequence of the fact that the electron is negatively charged. So in this situation, where the electron is spinning clockwise from above, the spin is, I suppose, strictly speaking, downwards in the negative z direction because the spin angular momentum vector is downwards. This comes from the fact that the right-hand grip rule applied to the supposedly spinning mass makes the thumb point downwards for the angular momentum. However, the magnetic moment is upwards, and this, of course, is on account of the fact that the right-hand grip rule applied to the supposedly rotating current makes the thumb point upwards. The negative spinning charge means the conventional current is in the opposite direction to the spin direction. So what do I mean by spin up or spin down? Do I mean the spin angular momentum or the spin magnetic moment? Well, as I mentioned earlier, I am more often than not going to take the magnetic moment direction as my direction for spin. This means that when the electron is placed in a magnetic field like this, which is pointing upwards in the z direction, and when it eventually comes to equilibrium in the lowest energy state like this, then the magnetic moment will point up in the z direction, and the spin angular momentum, of course, will point down. I am going to call this situation spin up, in accordance with the direction of the magnetic moment vector. If you don't clearly take this idea on board and you forget about it, there's a danger that later on in the discussion you start to think about actual spin, in other words spin angular momentum, and you'll start getting confused about direction. On account of the fact that much of our discussion will be about magnets and the like, magnetic moment will be the determining idea in my discussion of spin. There wouldn't be a problem, of course, if we were dealing with positively charged particles, because for them, spin angular momentum and magnetic moment would be in the same direction. But we will be dealing with electrons in the main, and with my convention, you must think in terms of magnetic moment when the word spin is mentioned. I will try on occasions to call it spin magnetic moment, but more often than not, the word spin alone will be used to mean spin magnetic moment. Okay, point made, I hope, for the last time. So with this measurement equation of quantum mechanics, probably the first thing we need to decide is what we're going to use as state vectors or wave functions or whatever you want to call it for states which will contain the possible information about spin. Remember, we're only interested in the spin direction of an electron. In a way, that's the only information the state vector needs to contain. We're not interested in velocity, momentum, energy, anything like that. We only need to be able to write down some kind of state vectors which indicate something about the spin of the electron. Then, if we can also find some kind of operators, we'll be able to apply an operator to a state and see if it gives a measurement. See if it gives the same state multiplied by some real number, the measurement. I said before that we only really need two basic states, one describing spin up in the z direction and one describing spin down in the z direction. That means we only need a two-dimensional Hilbert space for these states to reside in. Now realize that you might say, surely there are more than just two situations that the spin can be in. What about a spin to the right or the left? What about a spin at 45 degrees to an axis or whatever? Well, you'll see as we move on that we can actually get away with just the two. Spin up in the z direction and spin down in the z direction. It's a bit like when we have vectors in ordinary space and we resolve to other directions. So if we have just two basis vectors in this imaginary Hilbert space, we can make the state vector for any other situation. Anyway, more on that in a moment. Hopefully it will become clear. Okay, let's think about these up and down states in the z direction. In quantum mechanics, state vectors of Hilbert space are often written in a kind of shorthand. For example, states with spin up or spin down in the z direction could be written in this shorthand. Lowercase u and d are the standard way to do this, but I've decided to use capital letters for u and d in this notation, so that my shorthand for the states up and down in the z direction will be written like this. This kind of symbol would designate the spin up state in the z direction, and this the spin down state in the z direction. I'm using up and down, u and d as applying only to the z direction. The strange looking brackets in this shorthand are a standard notation introduced by physicist Paul Dirac. This particular type of bracket is known as a ket. I may say a bit more about this later, but for now I'll just say that we can put almost anything we want inside the ket bracket. The thing we put there is almost any kind of shorthand that will explain what the state is emphasizing or what it's about. It wouldn't contain numbers or variables or mathematical formula, it's just a label. I have put the simplest possible shorthand label for the up and down states, the letters U and D. I think I will also add a Z subscript to these, just to emphasize that by up or down, U and D, I mean in the Z direction. Now this shouldn't really be necessary because we've stated what our coordinate system looks like, but it might remind some people that up and down mean in the Z direction. And in any case, we're allowed to put what we like, whatever shorthand we like, inside the ket bracket. We could even put more detail inside it if we really wanted to. We could write these two states like this: electron with spin up in Z direction and electrons with spin down in Z direction. This ket notation, as I say, is simply a shorthand to describe what the state is about. So in a way, anything goes inside that bracket as a descriptor of what the state is about, and you don't multiply things inside the bracket. You can't do any kind of manipulation with what's inside these brackets. It's just a label. If, for example, you had the number 2, say we did, multiplying the up state, that would be fine. It just means twice the state vector for up in this imaginary Hilbert space. It just means having a vector twice as long, if I can use the word long about such a theoretical thing. You would not, however, then put the 2 inside the ket bracket. That would be silly. The UZ part of this is just a label. It's the whole thing that stands for the state that the electron is in. Its spin is up, for this state, in the positive Z direction. Okay, so these things are simply the shorthand descriptors for the two states that I am mainly going to be interested in. But what about the actual nitty-gritty of these states? What can I write down for what these things, these symbols, are equal to? I don't want it to be anything to do with momentum or distance or energy of the electron. I only want it to be about spin up or spin down. So my question here is, what can I say these things are equal to? What can I write down for each of these two particular state vectors, up and down? Well, a useful way to proceed is to use something that we might call a column vector. Again, there's a danger in using the word vector because if you haven't done quantum mechanics in a bit more detail, you may start to think in terms of vectors in normal space like force and velocity and momentum and so on. We don't mean vectors like that. We mean vectors in this imaginary space which we call Hilbert space. So we're going to use a column vector, or if you like, a column of numbers to denote the state that the spin is in. The numbers will tell us whether the spin is up or down in the Z direction. These two vectors in this imaginary Hilbert space will be written like this. The state which has the spin pointing up in the Z direction will be written as 1, 0. And the state with the spin pointing down in the Z direction will be written as 0, 1. Now this may seem strange, but it is really obvious and simple. It's less complicated than you might think. The top number in the column represents what you might call the upness of the spin state, and the bottom number in the column represents the downness of the spin state in the Z direction. So it should be clear, in this state it has, in a sense, in a very simplistic sense, complete upness and no downness. It is the state representing spin up in the Z direction. This state, on the other hand, has no upness and complete downness. This is the state representing spin down in the Z direction. I'm implying, of course, that 1 means complete contribution and 0 means no contribution. Now it's probably worth mentioning here that we like to work with states which are what we call normalized. This simply means that the sum of the squares of the numbers in the state vector here must be equal to 1. Now this is obviously the case for these two states. 1 squared plus 0 squared equals 1. Both of these states are what we call normalized. So that's no problem. On top of that, however, the squares of each of these numbers also represent something else important in quantum mechanics. They represent the probability of getting an answer to the question, what state is the electron in? What I mean is, if an electron is in this state and the spin is up, and if you measure the z component of the spin of this state, 1 squared is the probability that you will get the answer as +1, in other words, spin up. On the other hand, 0 squared is the probability of the answer down. Now that of course makes sense. It is the up state after all, so any measurement of the component of the spin in the z direction must 100% of the time give the answer up and 0% of the time give the answer down. Similarly for this state, the down state, 0 squared is the probability that a z component measurement on this state would give the answer up, whilst 1 squared is the chance of a down answer. Again, that makes sense. This is the down state. And that's it really for the states of the electron spin. These are what we call our two basis states of the electron, spin up and spin down in the z direction. In a sense, they define our two-dimensional Hilbert space. I could, I suppose, put a subscript z on the vector side of things just to remind us that we're dealing with the z direction and what the two numbers are about. But it's not really essential. In fact, none of the z's here, subscripts, are really essential. We shouldn't need a reminder that our up-down direction is along the z-axis. Having said that, I may include the subscript z on the vector side of things as well, lest we forget when we start talking about spins in the x and y directions later. What I mean is, they, the z's, may actually be especially useful as reminders when later on we make up other vectors in the Hilbert space by adding up different bits of these two. You know the way in ordinary space we can make new vectors by adding up vectors in the x, y or z direction? Well, in a similar way, here in Hilbert space, using these two vectors, we can add bits of them up to create new vectors in the two-dimensional Hilbert space. Anyway, you'll see, I hope, what I mean in a few minutes when we get to that. In a sense then, these two vectors in Hilbert space are all we're going to need. Our imaginary space where these state vectors reside, our Hilbert space, is only two-dimensional. These two state vectors represent the two dimensions. Now, in order to elaborate on this, let me first revert to thinking about ordinary, everyday, real space. When we deal with ordinary everyday vectors in ordinary three-dimensional real space, we say that x, y and z are the three dimensions. That would be the everyday space for distances or displacements and the like, and even for spin direction. We could, I suppose, define unit displacement vectors in these three directions, and in a sense they could represent this everyday displacement or distance space. These would be little vectors, 1 unit in length, which were pointing in the x or the y or the z direction. And we could probably write them as vectors in this way, and you've probably seen this kind of thing done before. The hat over the x, y and z simply indicate that they are unit vectors. They're 1 unit in length. Note, for those who might have done some quantum mechanics before, these hats here denote unit vectors in ordinary space, as is the notation in pure mathematics. People should not confuse them with the hat notation that's sometimes used in quantum mechanics for operators. The first number in the bracket represents the size in the x direction, the second the size in the y direction, and the third the size in the z direction. And you can see that they are unit vectors because for each of them the sum of the squares of their x, y and z components add up to 1. 1 squared plus 0 squared plus 0 squared in each case. These unit vectors in ordinary space, remember, are clearly at right angles to one another, or as we say, orthogonal to one another. Not only is that common sense from our knowing about three dimensions, but also you could show it mathematically by multiplying any two of these unit vectors together, and you'd get the answer 0. You do this, of course, by what we call the dot product or the scalar product in mathematics. And to get this, you multiply the numbers in the equivalent position together and then add the results to get the sum. If the vectors are orthogonal, then the answer will be 0. Here is that calculation for the multiplication of the unit vectors x times y, or x dot y. Taking the dot product, 1 times 0 is 0. 0 times 1 is 0, and 0 times 0 is 0. The total is 0. The two unit vectors are orthogonal, or if you prefer, they are at right angles to one another in real space. Any two vectors which give 0 when multiplied together in this way must be at right angles to one another. Now that's trivial, I know, but let me now go back to our Hilbert space. Here are the state vectors in our two-dimensional Hilbert space, nothing to do with ordinary space now. In a sense, these are the unit vectors that define the two-dimensional imaginary space of spin up and spin down. They shouldn't be thought of as distances in this imaginary space. The Hilbert space is to do with spin. Granted, it's to do with upness and downness as they relate to ordinary space in the z direction of ordinary space, but the Hilbert space of these two vectors is nothing like ordinary space. We should realize, though, that these two vectors are actually orthogonal. I won't say they are right angles because they're not in ordinary everyday space, and in any case, saying that would confuse things, as you'll see in a minute. These two state vectors are orthogonal. They are what we call the basis vectors of our space of states, our Hilbert space for an electron with regard to its spin. It's very easy to show that they are orthogonal to one another simply by taking what we might call the dot product of them. In other words, by multiplying the up state by the down state. If the answer to this product is 0, then the two states are orthogonal in Hilbert space. Actually, in quantum mechanics, we don't call it the dot product, we call it the inner product, but it's very like the dot product. And the multiplication is written like this. The first vector is written as a row vector, and the second as a column. In this case, the spin up vector is the row. 1 in the first entry means up. And the spin down vector is the column. 1 in the lower entry means down. Because all the numbers in this case are real, there are no imaginary numbers, it amounts to the same thing as the dot product in this situation. This different way of writing the upstate is called the bra vector, and it goes with the ket vector in this kind of product or multiplication to form what you might call the bra ket, which comes from the word bracket. It's written like that, in that backward way, just in case there are imaginary numbers in the state representation, in which case we would need to treat things slightly differently. We would need to take the complex conjugate of the numbers in the ket vector to use as the numbers in the bra vector. However, as all our numbers here are real, they're only zeros and ones, we can think of this multiplication as just like the dot product. Simply multiply the two things together as vectors in Hilbert space. If you know the rules for matrix multiplication, you'll realize it follows that kind of process too. First term times the first term, plus second term times the second term, and so on. Actually, there's no so on, because we've only got two dimensions, so we only have two terms. So it's 1 times 0, which is 0, 0 times 1, which is also 0, giving a total of 0. These two states, up and down, are clearly orthogonal in Hilbert space. They are kind of at 90 degrees to one another in Hilbert space, although I probably shouldn't say that. A word of warning, however, here, and here's something to get your head around, something which is very important to realize. Our two basis states are orthogonal. We've just established that. But when most physicists hear the word orthogonal, we think at right angles. Perhaps we shouldn't do that, but we do. These two basis states are orthogonal in Hilbert space, and in that simplistic sense they could be said to be at right angles to one another in Hilbert space. We've just shown that in a way that they are a bit like two ordinary vectors in ordinary space, which when you multiply them together give 0 as the answer. They are independent of one another. They are orthogonal. They are in a sense at right angles to one another in Hilbert space. However, these two state vectors represent two situations in ordinary space which are anti-parallel to one another. They are very much not at right angles in ordinary space. Think about that. This state vector in Hilbert space is for spin up in the z direction, and of course I mean magnetic moment up. And this state vector in Hilbert space is for spin down. These two state vectors are definitely orthogonal to one another, kind of at 90 degrees to one another in Hilbert space. But in real space, the spins that they represent are definitely not at right angles. They are anti-parallel. This can take some getting used to, thinking of these two states of the spin of an electron as being orthogonal as states in Hilbert space, and yet being 180 degrees different in real space. But they are. Try to remember that when I say something like this is orthogonal to that, and your initial reaction is to say, what? You need to remember it's the two state vectors in Hilbert space which represent these two spins which are orthogonal. Very important and easy to slip up when you first encounter the quantum mechanics of spin. Anyway, moving on. At this point I am in a sense all sorted as far as this side of things is concerned, the kind of state vectors I need in order to use this equation to measure spin components via the mathematics of quantum mechanics. I've got my two state vectors, one for spin up in the positive z direction and one for spin down in the negative z direction, and I've said that I don't need any more dimensions because I'll add bits of these two vectors to make new state vectors when I need them. All my vectors, state vectors, will lie in these two dimensions of Hilbert space. What we really want now is an operator that we can use to do the mathematical measurement of the spin. Before I get to that, however, I need just one more short digression. I would like to get a little bit into the idea about adding state vectors together to form new ones. In particular, I'd like to think about how we can make state vectors which represent spins in other directions in real space, directions other than the z direction. For example, can we write down a state vector for a spin to the right in the x direction? Well, I suppose one way to do it would be simply to rotate the whole system and imagine that positive x was the new up. That would be easy to do, but it would change the whole system. And I don't really want to do that. I want to stay with the idea that up means positive z direction, and so on. We obviously should stick with the z direction that we started all our definitions with. So my question is, can we write down a state vector for a spin, let's say to the right in the x direction, but using the z system, the z basis that we've already started thinking about? Can we add together bits of the two z states in Hilbert space, our basis states, the ones that we've already got? Can we make something which will represent a state vector with the spin in the positive x direction, in other words to the right? Your initial reaction might be to say no, especially if you're thinking in terms of ordinary space. You may be thinking that x is at right angles to z. How can you add two bits of z, up z and down z, to make x? You can't. And that's true, you can't in ordinary space. However, you need to remember that in adding the state vectors, we're not in ordinary space, we're in Hilbert space. Adding bits of these two basis vectors can actually produce a new vector in the same Hilbert space, but which represents a situation in real space which has the spin pointing in the x direction. In fact, different mixtures of these two basis states mixed within Hilbert space can produce states for any direction in real space. Let me, without justification yet, although we will get there, let me write down the answer for a mixture of the two basis states needed for a new state which represents the spin in the positive x direction, in other words to the right. I'm going to call it Rx, R for right, and x just as a reminder that right means in the x direction. Overkill, I know, but never mind. This is the state vector for an electron spin definitely pointing in the positive x direction, in other words to the right. It's 1 over root 2 fraction of the up state plus 1 over root 2 fraction of the down state. In a naive sense, this particular state vector seems to be represented by 1 over root 2 amount of upness and 1 over root 2 amount of downness in the z direction. And yet, it's supposed to be, and in fact it is, the state with the spin pointing to the right in the x direction. Our minds, I think, get confused by thinking in ordinary space and things being at right angles in ordinary space or at 180 degrees different in ordinary space, and we can't really feel what the addition of states in Hilbert space is really like and what it would produce in real space. All I can say for the moment is that this is correct, so you need to stick with me for the moment. It will seem more reasonable later, I think, as we investigate things. Let me also write it in a different way before we move on. I think you can see that these two vectors could be written as up and down in our z system, so that the state vector for the spin definitely pointing to the right in the x direction could also be written like this. Finally, I suppose, we could have added the two parts together into one column vector, in which case there's another way in which we can write the state which is representing a spin pointing to the right in the x direction, and that's like this. These three are all the same, but the version we'll probably most often use will be this kind of format, which can also be written like this. Let me emphasize this point. The state which represent the spin in the positive x direction, and as I say, I've put an x there here to emphasize that, can be written as some kind of mixture of the state of the electron pointing up in the z direction and pointing down in the z direction. We mentioned normality in passing before, and if you've remembered that, you realize that this right pointing state is actually normalized. The squares of the coefficients of the up and down states add up to 1. 1 over root 2 squared plus 1 over root 2 squared is a half plus a half, which is 1. As before, these coefficients of up and down states also have another significance, however. Take, for example, the coefficient here of the up state contribution to the right state, which is 1 over root 2. The square of this, which is 1/2, is the probability that if this right pointing x directed spin is measured in the z direction, it will yield an answer that the spin is up in the z direction. I'll say that again. It's a spin pointing definitely in the x direction to the right. But if you then measure the component of that spin in the z direction, there is a 50% chance, probability a half, that it will give the answer to that spin as being up in the z direction. Similarly, of course, the coefficient of the down vector is 1 over root 2. So again, square that, there's a 50% chance that it would be measured as spin down. Now that ties in with what we've been thinking about in connection with spins and magnetic moments. If an electron is prepared in such a way that its spin is in the positive x direction, in other words to the right, and you then measure the component of the spin in the z direction, there's a 50% chance that it will be spin up and a 50% chance that it will be spin down. That was for the right state. However, in exactly the similar way, it turns out that the state vector representing a spin in the negative x direction, in other words to the left, contains minus 1 over root 2 amount of upness in the z direction and 1 over root 2 amount of downness in the z direction, if I can call it if I can use that rather loose language. It's different to the right vector by a negative sign in the up vector part. Once again, that probably won't make much sense to us at this stage, because in trying to think about it, our mind can't easily jump from Hilbert space to ordinary space and work out what's going on. However, having accepted the right vector structure, if you have accepted it, the form of this left vector can probably be accepted fairly easily. For similar reasons, of course, we can write it in other ways, as a mixture of the column vectors of the basis, or by adding those two column vectors together. Notice again the minus sign in the top entry. That's how it differs from the right pointing state. Let me write out those two states, left and right, once more. Here they are in one particular way of writing them. And there, in some ways, is what they represent in real space. Spin to the right and spin to the left. These spins are 180 degrees different in their directions in real space. But what about these vectors in Hilbert space? If you're ahead of me, you've probably realized that these are orthogonal to one another in Hilbert space, or if you like, at 90 degrees in Hilbert space, even though they're 180 degrees in real space. Let's check. Let's do the dot product of the two, or rather what I should call their inner product in Hilbert space. Right times left. I'll write it like this. The bra for the right multiplied by the ket for the left state is the right state written as a row vector, which has 1 over root 2's as both being positive, multiplied by the column vector for the left state, which has the minus sign in the up part of it. Now this multiplication isn't difficult. You just do the usual, take the first one times the first one and add to the second one times the second one. So it's 1 over root 2 times minus 1 over root 2, which is minus a half, plus 1 over root 2 times 1 over root 2, which is plus a half. Add them together and the total is 0. That means that these states are indeed orthogonal in Hilbert space, even though they represent right and left in real space. If you really think about it, at least the mathematics should be obvious, even though it can be mind-boggling at first, jumping from one space to the other in your mind. Now, before we move on to the y direction and think about how the in and out states could be formed from our two basis states of up and down, I want to try to make a representation of this Hilbert space, which we might call our spin space. Even though it's a mathematical abstraction, we know it's two-dimensional. So I can draw a representation of it in the plane of the screen. So here it is. I've got two axes in 2 dimensions, so what should I call them? Well, I know that the up and down states are perpendicular or orthogonal in Hilbert space, so let me pick these two. These are what we are calling our basis states. Now that might look strange at first. One naturally tends to think of down as being the negative of up on the same axis. But of course that's in real space. Here, down and up are at right angle or orthogonal in Hilbert space. Now the state vectors are each a kind of unit vector in that they are normalized, so I suppose I shouldn't label the axes with these terms, but rather with something else, maybe just up vector and down vector. And then if I want to, I could put the state vectors, the basis vectors, in like this as little unit vectors on each axis. Note that this is the positive up vector direction and this is the negative up vector direction. Negative up in this sense does not mean down. A vector arrow in this direction would simply mean the up basis state will be multiplied by a minus number. This is minus 1 times up, whereas this is minus 2 times the up vector. However, perhaps for simplicity, I will label the axes in this Hilbert space with the state vectors, the unit vectors. A bit naughty, but it makes the diagram a little bit cleaner. So what about the right and left states? Can we show these two states in this Hilbert space? Well, we know, or at least I told you, that the right state is a mixture of up and down like this. It's 1 over root 2 times the up state plus the down state. So it would be natural to think that the right state is some kind of vector addition of up and down in this two-dimensional Hilbert plane. In fact, the 1 over root 2 should point to the idea, perhaps, of sine 45 degrees and cos 45. So it would make sense to put the right state vector in the upper quadrant at 45 degrees to the up state vector axis. There. This is in the plane of the screen. It's not into the screen. And once again, I'm probably wrongly labeling the axis by the unit state vector, but it's for simplicity. Then by simple geometry, we would say that the right state was a mixture of the up and down, and the multipliers of each of them is cos 45 and sine 45, just like taking components. Similarly, as the left state is only different from the right state by having a minus sign for the components of the up part of it, we would probably show the left state as being in the lower quadrant of Hilbert space. There. Now in one way that makes sense. We've just shown that the left and right states are orthogonal to one another, and here they are at 90 degrees to one another in our picture of Hilbert space. As I keep saying, the difficulty for us is that we have to jump in our minds from real space to Hilbert space and back again, and we often lose the consistency and common sense of the mathematics. Here, the left and right spins are at 180 degrees to one another in real space, but the state vectors of them in Hilbert space are at 90 degrees in the sense that they are orthogonal. Anyway, we've now got the states for up, down, left and right. But what about the third dimension in real space? What about the state vectors for the spin when it is in or out? In other words, in the y direction in real space. We can write down these fairly easily enough, although it's not so easy to give simple arguments as to what they mean. Here are the state vectors for spins in and out of the screen. In other words, in the positive and negative y directions, and they're written in terms of our up and down basis vectors, our z direction states. Again, I've given them letters I and O for in and out, but I've also added the subscript y as a reminder that these states represent the spins in the positive in and negative out directions in real space. Now, if you look carefully at these, they are very similar to the right and left states that we've just been looking at, in that they are a mixture of up and down spin states, the two basis states. However, you'll notice that there is an I, a square root of -1, in the downness side of things, and also the signs are different, +1 and -1 for the other. Quite what the I denotes in our simple picture of two-dimensional Hilbert space is not clear without pursuing the mathematics further, and that would not really be helpful. The truth is, instead of calling our Hilbert space a two-dimensional vector space, I should have called it a two-dimensional complex vector space. I probably shouldn't say this, but it's as though there's a third dimension, one in which we could imagine the I direction to be in, a bit like with complex numbers and the Argand diagram. Anyway, for simplicity, we'll just take it as it is, and I won't attempt to draw a third dimension in my Hilbert space diagram, but simply accept that there is another set of values, the I values, in the space, in this two-dimensional space somewhere. What we could just mention is the other ways of writing the in and out state vectors. Just as with the right and left vectors, they can be written as a mixture of the column vectors that form the basis, or by adding those two column vectors together to form a single vector. And as in the case of the left and right states, even though the in and out spins are at 180 degrees to one another in real space, their state vectors are orthogonal in Hilbert space. This is easy enough to show by multiplying the two vectors together in their column vector form, just as we did before with left and right. This amounts to taking their inner product or their dot product. I mentioned earlier in passing, however, that whenever you do this, you must take the complex conjugate of the bra vector, the first vector. Now that hasn't mattered so far in earlier examples for left and right because everything was real. But here we have some imaginary coefficients. The upshot is that instead of plus I here in the downness part of the instate, which is what it normally is for the instate, we have to put minus I. The outstate already has a minus I, so that's okay. Working through this inner product, it is 1 over root 2 times 1 over root 2, which is half, plus minus I over root 2 times minus I over root 2, which is minus a half. The total is 0. The two states in and out are definitely orthogonal. It's a pity that I can't draw them on my picture of Hilbert space. Once again, of course, as in the case of the left and right states, the coefficients of the up and down components of these in and out states have a great deal of significance. Take, for example, the in state, which I'll show in this form. Looking at the two coefficients, we can see that the state is normalized. This means that the sum of the squares of the coefficients is equal to 1. However, now that we have a complex, or rather imaginary coefficient, the so-called square of this one has to be found by multiplying it by its complex conjugate. So normalization of the whole thing is shown by taking 1 over root 2 squared and adding the product of I over root 2 by minus I over root 2. Anyway, the total gives you plus 1. The state is normalized. And the same idea goes for the probabilities. If you have an electron in this state, its spin is definitely pointing into the screen in real space. However, if you then measure the component of the spin in the z direction, there is a 50% chance of the spin being up in the z direction and a 50% chance of it being down. The so-called square of each of the components is a half, remembering here to use the product of the coefficient times its complex conjugate for the one with the I in. This is another stark reminder that you can never get 0 for a measurement of the spin component of an electron when you measure it in any direction. In whatever way it has been prepared, it will always measure either fully in the direction you're looking at, that's plus 1, or fully in the opposite direction at 180 degrees, that's the minus 1, never 0. I'll just remind you that this is because we're dealing with spin-a-half particles in terms of angular momentum. They have two values only for any component of their spin angular momentum, plus h bar over 2 and minus h bar over 2, opposite direction. Any measurement of any component can never give 0 as the answer. It can never be measured as 0. In our discussions, however, we talk about measuring the spin as 1. So the possible components are plus or minus 1 rather than plus h bar over 2 and minus h bar over 2. We're connecting more with the spin magnetic moment rather than spin angular momentum. That was just a reminder. Anyway, accepting all that we've done in defining these states in terms of the two basis states of up and down, we can write out our 6 states of up, down, left, right, in and out, all written in terms of what I loosely call upness and downness in the z direction. Here they are all together in their various forms. These are the two basis states, the state vectors which definitely stand for spin up and spin down in the z direction of real space. These states define the Hilbert space in which we're working, and although the spins that these two states represent are anti-parallel, or 180 degrees to one another, the states in Hilbert space are orthogonal, or as we tend to imagine, at right angles to one another. The two numbers which make up the state can be thought of, in very simplistic terms, as the amount of upness of the state and the amount of downness. In these cases, there's complete upness in one and complete downness in the other. These are the mixed state vectors for spin definitely in the x direction of real space, left and right. But again written in the z system of Hilbert space, they are a mixture of the basis states up and down. Once again, the spins that these two states represent are 180 degrees to one another in real space. but the states in Hilbert space are orthogonal to each other. These two states in Hilbert space can easily be pictured as being in the plane of that two-dimensional imaginary Hilbert space. And these are the mixed states for spin definitely in the y direction of real space, in and out of the screen, but again written in the z system of up and down. This is very similar to the mixture of states for the x direction, but they have the negative sign in a different place and they have an I hanging around the square root of -1. Again, these spins in real space are clearly at 180 degrees to one another, in and out. The states in Hilbert space are orthogonal. However, we weren't able simply to imagine how these two states could be situated in our two-dimensional Hilbert space diagram because of the presence of the square root of -1 in the coefficient for the downness part of the state vectors. Anyway, I simply wanted to show that you can use the z system, the z basis of states, for other state vectors representing spin in other directions of real space. In fact, this idea of the column of two numbers representing what I probably shouldn't call upness and downness in the z direction can be used to write down any definite state of the electron in any direction of real space, not just the x and y directions. So even though we're using what I might call the z system, we can use this to represent spins pointing in any direction in real space. For example, if we wanted to know the state vector for a spin in the xz plane of real space, ignoring y in this example, and suppose a spin was pointing at 45 degrees to both x and z. The red arrow here represents that spin vector in real space and is in the plane of the screen. It's not pointing into the screen. For a spin magnetic moment definitely pointing in this direction, it clearly has more upness than downness in the z direction of real space. And in fact, the rules and mathematics of quantum mechanics give the state vector as 0.924 up and 0.383 down. We can write it in these two ways, of course. Spin with state of 45 degrees to the z-axis is the column vector 0.924 and 0.383. Or it's equal to 0.924 times the up state plus 0.383 times the down state. And all of this can be shown from the mathematics, but it shouldn't at this stage seem too unreasonable. What I mean is, when a moment ago we looked at a spin in the x direction, it seemed obvious that if you're going to try and write the state as a mixture of up and down, then there should be equal amounts of each, namely 1/√2 for each of the two coefficients. It's obviously at 90 degrees to the z-axis and pointing in the positive x direction. However, in Hilbert space, that same spin vector was represented as a state vector at 45 degrees to the up state and 45 degrees to the down state, which themselves were at 90 degrees to each other. These two diagrams, in a sense, represent the situation for a state with equal upness and downness. One is the diagram representing the spin vector in real space, and the other is the diagram representing the state vector in Hilbert space for the same situation. Do you notice the way for this x direction spin, the angles seem to be halved between real space and Hilbert space? What is 90 degrees in real space between the spin vector and the up direction is 45 degrees in Hilbert space between the spin state vector and the up state vector. It probably should seem reasonable, therefore, that if the spin vector in real space is at 45 degrees to the z direction, which is half of 90, then the angle in Hilbert space between the spin state vector and the up state vector should be 22.5 degrees, which is half of 45. You may have realized that this situation of a spin vector in real space which is at 45 degrees to the z-axis is similar to a situation we had earlier when we were looking at some imagined electrons passing through the Stern-Gerlach apparatus. If you need to, you can refer back to that video, but in one of the situations we looked at, we imagined the electron spin or magnetic moment to be at 45 degrees to the vertical, just as we have here. We then made the statement that when they passed through the Stern-Gerlach apparatus, 85% or so went upwards and 15% went downwards. This is obviously to do with the fact that we had a mixed state, some upness and some downness in the mathematics. In other words, there is a chance of each electron being considered to be already pointing upwards, already in the up state, and a chance of them being considered to be already pointing downwards, already in the down state, even though we knew that they started off 45 degrees to the vertical. But what is this chance? What are the probabilities of such an electron to be measured as up or down? How do you work out the probabilities from the quantum mechanics? Well, the Hilbert Space diagram gives a hint. If we're going to try to find the coefficients of what I've been loosely calling the upness and downness of the state representing this real space situation, we need to use the Hilbert Space diagram and not the real space diagram. This is the state vector in Hilbert space, which represents the real space 45 degree situation. And from this Hilbert space diagram, the up component of this state vector in Hilbert space is cos 22.5 degrees, and the down component of it is sine 22.5 degrees. So the state vector for this situation, this red arrow representing the spin state, could be written as state with spin of 45 degrees to the z-axis real space equals cos 22.5 times the up state plus sine 22.5 times the down state. Evaluating the cos and sine functions gives for the two coefficients 0.9424 and 0.383. Now, the sum of the squares of these two coefficients obviously add up to 1. Sine squared plus cos squared of any angle is 1. So the state is automatically normalized. However, we also said that each individual coefficient squared is the probability that this 45 degree pointing spin vector would be considered to be pointing up or down. In other words, 0.924 squared is the chance of it being measured as up, and 0.383 squared is the chance of it being measured as down. This gives about an 85% probability for up and a 15% probability for down. So if we started with 100 electrons, all at 45 degrees to the positive z-axis, and they went through some imaginary Stern-Gerlach apparatus, then about 85 of them would go up and 15 would go down. Similarly, the mathematics of quantum mechanics here predicts that there is an 85.4% chance of any single electron being measured as up and a 14.6% chance of it being measured as down, even though the electron was known to be at 45 degrees to the z-axis, the up axis. More generally, of course, if we had a spin vector at theta degrees to the z-axis in real space, then the angle between the state vector and the up state would be theta over 2 in Hilbert space, and we could write down the state vector at theta degrees to the z-axis as cos theta over 2 times the up state plus sine theta over 2 times the down state. Or in column vector terms, it would simply be the column vector with cos theta over 2 in the upper position and sine theta over 2 in the down position. You probably realize that from this way of thinking, it's possible to produce a state vector for an electron with its spin pointing in any direction in real space. It's just a case of adding the basis vectors in Hilbert space in the right way, and it usually involves an angle somewhere or other. We could, of course, write a very general state for an electron, which would be at some angle to the x, y and z axes in real space, and that would be a times the up state plus b times the down state, where a and b could simply be real or they could be complex numbers. To make it look more general, we could write it like this: a1 plus ia2 times the up state and b1 plus ib2 times the down state, where a1 and b1 are the real parts of the coefficients and a2 and b2 are the imaginary parts. And these A's and B's can take any values as long as the state is normalized. In other words, as long as the sum of the squares of the coefficients add up to 1. Of course, by the square of a complex number, we mean the number times its complex conjugate. So the condition for normalization of this general kind of state would be A times A star plus B times B star equals 1. Or this expansion of it, which turns out to be the condition A1 squared plus A2 squared plus B1 squared plus B2 squared equals 1. I hope it's obvious by now that if you had a general state such as this, which had definite values of the A's and B's, but you didn't know what they were, then you would not know which direction the spin was pointing in. It would be a bit like our hypothetical imagining of an electron in a paper bag. It's there, we can't see it, and unless we know something about its history, we can't know about its spin until we measure it. It would, however, be pointing in some particular direction, in the sense that if we measure the components of the spin in that direction, we would be assured of the answer +1. But it's just that you wouldn't know which direction if you didn't know the A's and the B's or the history of the particle concerned. If, however, you then made a measurement of the spin in a particular direction and you just happened to pick the direction it was pointing in, you would definitely get the answer +1. Notice I'm saying +1 rather than h bar over 2. If, however, you happen to pick any other direction for your measurement, there would be some probability, some chance that you would get +1 and some probability that you would get -1. And these two probabilities would depend on the angle between your measurement and the actual direction of the spin, which you wouldn't know, of course. Measuring at 90 degrees to the spin would give you a 50-50 chance of getting the result +1 or -1. As we've suggested before, you could only be sure you'd found the direction of the spin if you had lots of identical electrons like this, with the same A's and B's all pointing in the same direction as this state. And you could then do a series of experiments on groups of them to home in on the actual direction of the spin, and then you could be fairly confident that you'd found it. I'm sure and I hope that you're beginning to realize how important it is to be aware of this whole idea of the mixing of states. Most people, even physicists, tend to think classically about most things in everyday life. When we make a measurement, we think in terms of having a definite value, and having that definite value even before it's measured. We tend to think that things have a measurement, even though we may not know it yet. That, of course, is not always the case with the physics of the very small and quantum mechanics. Of course, as we've just mentioned, things can have a definite value before a measurement is made, and we can even know what that value is. We could, for example, ensure that an electron had a definite spin direction, say to the right, by leaving it for a while in a strong magnetic field pointing to the right. Taking it out of the field, we can then be sure that if we were to measure the components of the spin in the x direction, it would definitely turn out to be positive, which means the spin is to the right. The problem, of course, is that if instead we measure the components of the spin of this electron in some other direction, any direction, but let's say the z direction, then the electron has to be considered to be a mixed state as far as our z basis is concerned. Being in the x direction, and therefore at right angles to the z direction, the coefficients of the mixed state would each be real and have a value of 1 over √2. Measuring the spin in the z direction would then mean that we would have a 50% chance of getting positive z spin up as the answer, and a 50% chance of negative z spin down. Only making this measurement once means we wouldn't know what the spin had been before we made the measurement. We'd have no clue that it had been in the x direction. We would need to do lots of similar experiments at different angles on identical electrons to work out what the spin had been beforehand, and from those lots of experiments we'd be able, with a little thought, to work out the probabilities and hence the original direction. We can make the same argument the other way around, of course. Namely, if we first make sure that an electron has a definite spin, say upwards in the positive z direction, then we can be sure that if we measure it in the z direction, it will definitely give us the result that the spin is up, positive z, 100% probability. Once again, however, the problem comes when we try to measure the component of the spin of this electron in any other direction, say, for simplicity, in the x direction. Then it would have to be considered to be a mixed state of what we might call the x system. Now, we haven't discussed the x system, but we can work like that. I suppose it should be obvious from our Hilbert space diagram, for instance, that you can make the up state out of the right state minus the left state, so that the up state can be thought of as a mixture of right and left. From that, it should then be obvious that with this measurement in the x direction, there'd be a 50% chance for positive x spin right and a 50% chance for negative x spin left. We will, of course, always be using the z system. And although I don't intend to talk about an x or y system for the basis states, I'm sure you realize that the mathematics is essentially the same. If you know the spin is in a particular direction, then it will always give that as an answer if you measure the spin component in that direction. However, if you try to measure it in any other direction, there will be a chance that the spin will be positive in that new direction or negative in that direction. The probabilities will, of course, depend on the angle between the original direction and the direction being measured, and this angle will involve being halved. The more these ideas begin to sink in to your understanding, the more you will take for granted the fact that if you had a single unentangled electron and had no idea about its direction of spin in real space, there would be a direction in space where, if you measured the component of the spin in that direction, it would definitely produce an answer of +1. It would measure the spin as being in that direction. In other words, there is a direction in space in which the component of the electron spin in that direction is certain. When later we look at a bit more of the mathematics of quantum mechanics, we'll be able to demonstrate this mathematically, that an unentangled electron has a definite spin direction in real space. But anyway, as I indicated earlier, this whole idea of mixing of states is very important in quantum mechanics, and we will return to it later. At this stage, however, I've probably flogged this horse to death. In any case, for the moment, we only really need to concentrate on the states for up and down in the z direction, which in terms of column vectors in Hilbert space are these. Remember, this whole system of column vectors that we are using is based on the z direction in real space, and that's why I've added the z subscript to these brackets. So we have what we might call our two basis states for spin up and spin down in the z direction. They represent spins that are up and down on the same z-axis of real space, but the state vectors themselves are at right angles, or strictly speaking orthogonal, in Hilbert space. That's enough, I think, for this video, but in all honesty, we haven't finished with the mathematics of quantum mechanics. We've got our two main states, up and down in the z direction, and we've also got ways of writing other states, right and left, and so on. We also know that those states actually contain the relevant information about the spin direction of the electron. What we now need is a way of getting that information out mathematically from the states. We need some spin operators which we can apply to these states, which will hopefully give a measurement of the spin of the state, and that will be for the next video in this series.